Hello everyone, my name is Akshay Shetty and this is my presentation for the signature project, that is the final project in the DA 5030 course. So to start off with, I'll talk a little bit about the dataset that I have chosen, which is the Wisconsin breast cancer dataset that I got from the Kaggle repository. There are 10 different attributes in the dataset, such as the radius, the texture, the parameter, the area, the smoothness, and various others. These parameters have three different attributes as well, which is the mean, the standard error, and the worst parameters. So let's start off by loading the dataset into our studio. Use the read CSV function. You can see that there's a diagnosis column. We're going to use this column for to predict our models. So we'll explore the data set a bit. We'll see the structure of the data set. It has 33 variables. The first, the diagnosis column, is the character variable, which we'll be changing into factor. The last one is the logical variable x, which we will have to remove because it has all NAs in it. And we'll also remove the ID column because it doesn't make sense to keep the ID column. So first we'll convert the diagnosis column into factors by using the factor function. So here you can see that, and we've also changed the names from B to benign and M to malignant, which is the type of the cancer. So we'll see the distribution of benign and malignant in the dataset, which comes out to be around 62%, 62.7% benign, and 37% of the patients are malignant. So now we'll take out the ID and the X column by cleaning the dataset, and we'll store it in a new cleaned data frame. So when we run this, you can see that the ID column has been removed and the X column also has been removed. Now we just have 31 columns to work with. So first of all, we'll plot a correlation. We'll do the correlation analysis for this dataset, which is this. If I zoom it out, you can see that there are a lot of highly correlated functions in this dataset right now. So we'll have to remove those. But this is a correlation plot of all the three parameters, that is the standard error, the worst, and the mean. So we'll take a look at all the different parameters separately. We'll take a look at the correlation plot for the mean parameter, then a correlation plot for the standard error parameter, and for the worst parameters as well. You can see the running code as well. This is it. So now we'll have to remove the outliers, which I think would be the highly correlated functions in this. So I've kept the cutoff at 90%, and I've created a new correlation breast cancer dataset, which would include only the variables from 2 to 31. So if I do this, I get 10 highly correlated variables. So we'll now remove all the highly correlated variables, which would imply that we've removed all the outliers from the dataset. Here you go. We have now created a dataset with all the outliers removed, which would better suit the machine learning model that we have. So now let's create. Now this is the correlation plot that I've created for the new dataset, new cleaned dataset without all the outliers. This looks much better than the one that we created earlier without cleaning the dataset. So now we can apply machine learning models on these. But before that, let's include the diagnosis column, which we removed from the dataset. So if we run this, the diagnosis column is included back, and we have 22 columns again. We had 21 before this. So normalizing, I've used the principal component analysis for normalizing the dataset. I've used the clean data frame that we had earlier to normalize everything. When we run this, we use the PRCOM function to perform the principal component analysis on the dataset. If you take a look at this graph, you can see that 90% of the data has been conveyed by the first 7 principal components that we have. And if you see the importance of the components, you can see here that 90% of the proportion has been explained by the principal up to principal component 7. So now moving on to model construction and evaluation, we'll first create the training and testing validation data sets. I've created a 70-30 split in the training and validation data set. The 3 models that I have created is KNN, Random Forest, and SVM model. So this is the link to the video that I have referred to while creating these models. All the models have been created with the same method. It's a very simple method. It is also used for cross-validation. I've also used the cross-validation function together while creating the models. It's a very simple method. We just have to change the method here from KNN to random forest or SVM, radial, or whatever function, whatever machine learning method that you're about to use. So firstly, we create a train control function for cross-validation. The method here is CV, which is cross-validation. The number is 10 because we are performing a 10-fold cross-validation. So we're going to run this. The pre-proc options is used to pre-processing and is passed using this function. So now we'll train our KNN model. We'll first get the KNN model. So we'll train using the train data that we've created here, and the method is KNN. You can see here the pre-process, that is enter and scale. We use the pre-proc options here, and the training control is the control part 1. So once we've trained this model, we'll now predict it based on the validation data set that we have. So as you can see here, we have a 94.12% accuracy when it comes to the KNN model, which is pretty good, and it has 0 false negatives, which is another plus point. So now let's take a look at the random forest model. It is the same method. We just have to change the method here from KNN to RF, which is random forest. The random forest takes a little bit more time to run and to compute than the other 2 models. Now we'll predict the model based on this. The random forest model has an accuracy of 95.29%, which is better than the KNN model, but it has 1 false negative, which doesn't look good because false negatives are never good. It has 7 false positives compared to the 10 that KNN had. It has 95% accuracy. And let's take a look at our last model, which is the SVM model. So we'll train the model here. We'll predict the accuracy here, and the accuracy comes out to be 96.47%, which is the highest of the 3 models that we have. And it has 2 cases of false negatives, but the accuracy is high. So let's compare the 3 models, and the model with the highest accuracy is, of course, SVM model, as we saw above. So as far as the model accuracy is concerned, 96.4%, 96.5% is a good accuracy to have, but we'll still create an ensemble model to see if we can improve on the accuracy that we already have. I tried creating an ensemble model using the Carrot ensemble package, but it was throwing some errors, showing that it had difference of levels in some parts. So I used a normal implementation by creating a cumulative predictor using the 3 predictions from the normal models, and then testing it on the validation data set. So when we run this, let's see if it improves the accuracy. It's giving us the exact same accuracy that we had in our SVM model. So it might be useful in other cases to create an ensemble model, but the dataset that I've chosen and the models that I've created provide you with decent accuracy. And so this was my project, and this is the accuracy that I've gotten. So thank you so much, and please, if you have any reviews or if you have any comments to help me improve my model, they'll be more than welcome. Thank you so much. Have a good day.